In the last class, we got the expression for average energy of an oscillator. So average energy of the oscillator, we got expression as average energy E is equal to h nu divided by e power h nu by kt minus 1. This is the expression we got, equation number 3. Now the number of oscillators, the number of oscillators in the frequency range, the number of oscillators in the frequency range nu and nu plus d nu is. So here the number of oscillators is given by 8 pi nu square d nu by cq. This is equation number 4. So why I am calculating all these? In order to calculate spectral energy density. So spectral energy density, spectral energy density, so can be obtained. See here, spectral energy density can be obtained by multiplying average energy. It is obtained by multiplying average energy of the oscillator, means equation 3, and number of oscillators. Number of oscillators is given by equation 4. So we'll multiply equation 3 and equation 4 to get spectral energy density. Now spectral energy density. So spectral energy density E nu d nu is given as by multiplying these two. So we'll multiply these two, h nu divided by e power h nu by kt minus 1 into 8 pi nu square d nu by c cube. D nu by c cube. So what we'll get if I multiply these two? So we'll get it as 8 pi h nu into nu square, a nu cube d nu divided by c cube e power h nu by kt minus 1. So this I'll write it as, so see here, this I'll write it as E nu d nu is equal to 8 pi h nu cube by c cube into d nu by e power h nu by kt. So this is the expression for spectral energy density. So this is equation number 5. This we call it as Planck's radiation formula. Planck's radiation formula, which holds good for shorter and longer wavelengths. Means it can explain shorter wavelengths and longer wavelengths. So how to believe that this expression holds good for longer wavelengths and shorter wavelengths? So if it can prove Planck's, if it can prove black body laws, means if it can prove Wien's law and Rayleigh-Jean's law, then we can say that this holds good for shorter and longer wavelengths. Okay, now we'll do derivation of black body radiation, derivation of black body radiation laws, using Planck's law, black body radiation laws using Planck's law. Okay, now if I see black body radiation laws from Planck's law. Okay, first one is Wien's law. We know that Wien's law holds good for shorter wavelengths. It holds good for shorter wavelengths. Okay, now this expression is in terms of frequency, nu. So how frequency and lambda are related. Nu is equal to C by lambda. Means frequency is inversely proportional to wavelength. So if wavelength is short, what about frequency? Frequency is large. So this numerator value is large. So what happens? H nu is greater than kT. Means numerator is very much greater than denominator. So H nu by kT, this kT this side. So it is very much greater than, it is very much greater than 1. So implies here e power h nu by kt is there. So e power h nu by kt is much greater than 1. So here e power any factor more than greater than 1. If I take e power term, then it is much greater than 1. So when compared to e power h nu by kt, when compared to e power h nu by kt, neglect 1. So in above equation 5, when compared to this term, you neglect 1. So what happens to this equation? So equation 5 reduces as, e nu d nu is equal to 8 pi h nu cube divided by c cube into d nu divided by e power h nu by kt. E power h nu by kt, because 1 is neglected. Okay, now I want to convert. See here, I want to convert, means e nu d nu is equal to, I want to write it as 8 pi h nu cube by c cube into d nu into this to numerator. So what happens? E power minus h nu by kt. This becomes e power h nu by kt. Now I'll convert nu in terms of lambda. So nu is equal to c by lambda. So what will be d nu? Modulus of d nu will be, here c is constant. C is the velocity of light. So only differentiation should be done with lambda. What is the differentiation of 1 by lambda? Minus 1 by lambda square. So minus c by lambda square into d lambda. Okay. So substitute all these values. Substitute all these values in above equation. So if I substitute all these values in above equation, I get it as E nu. So instead of nu, I'll write lambda. E lambda d lambda is equal to 8 pi h nu. Nu cube can be written as c cube by lambda cube into c cube into d nu. D nu can be written as modulus, means positive, c by lambda square d lambda into e power minus h c by lambda kt. Okay. So I have substituted in place of nu c by lambda. So I'll get it as e lambda d lambda is equal to, this c cube get cancelled. C cube get cancelled. We are left with 8 pi hc by lambda power 5 into e power minus hc by lambda kt into d lambda. Okay, I can write this expression as e lambda d lambda is equal to 8 pi hc. 8 is constant, pi is constant, h is constant, c is constant. I'll write it as c1. This lambda power 5 to numerator, lambda power minus 5. E power minus, see here, minus h is constant, c is constant, k is constant. So c2 divided by lambda t. c2 divided by lambda t into d lambda. So what we have written, e lambda d lambda is equal to c1 lambda power minus 5 exponential minus C2 by lambda T into d lambda. So this is nothing but, if you check in Wien's law in black body radiation, this is Wien's law for energy distribution. So this is the Wien's law for energy distribution. So you can check in the black body radiation. We have done in the black body radiation. You can check for that. Okay, means we, from the Planck's radiation formula, from this Planck's radiation formula, we were able to get Wien's law, which holds good for shorter wavelengths. Means it can explain for shorter wavelengths. Okay, like this only we'll check for longer wavelengths. Okay, now we'll check for longer wavelengths. Now okay, we'll check for longer wavelengths. Okay, now for longer wavelengths, that is Rayleigh Jean's law. Okay, now we know that longer wavelengths, it holds good for longer wavelengths. Now if wavelength is more, so if wavelength is more, if lambda is more, what about frequency? Frequency is small. So if wavelength is more, frequency is small. If frequency is small, the numerator term h nu is so this h nu will be less than kt. So h nu by kt will be less than 1. So e power h nu by kt will be less than 1. So what happens is e power h nu by kt, this can be expanded. This can be expanded in Taylor series. Okay, if I take e power x, what is the expansion of e power x? 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on. But here x is very much small. Means if x is 0.1, what will be x square? 0.01. So x square will be still more short. So we can neglect higher order terms. So we can neglect higher order terms. So e power x becomes 1 plus x. So what I can write, e power h nu by kt is equal to 1 plus h nu by kt. So e power h nu by kt is equal to 1 plus h nu by kt. Okay. Now what happens here? So e power h nu by kt is equal to 1 plus h nu by kt. Now substitute this in equation 5. So this is equation 6. So substitute 6 in equation 5. Means we can substitute this in Planck's radiation formula. So see here, this is the Planck's radiation formula. If I substitute e power h nu by kt, you can substitute as 1 plus h nu by kt minus 1. Okay. Now, so I will substitute here. So I'll get it as E nu d nu is equal to 8 pi h nu cube by c cube into 8 pi h nu cube by c cube into d nu by 1 plus h nu by kt minus 1. So plus 1 minus 1 get cancelled. So you'll get it as E nu d nu is equal to 8 pi h nu cube by c cube into d nu into kt by h nu. This denominator term becomes numerator. Okay. Now we know we want to substitute in place of nu c by lambda. So in place of nu c by lambda. So what happens to modulus of d nu? Modulus of minus c by lambda square d lambda. So you substitute this. We'll get it as e lambda d lambda is equal to 8 pi h. In place of c nu cube, you substitute c cube by lambda cube into c cube into, what is this one? D nu. D nu is c by lambda square into d lambda into kt divided by h c by lambda. Now if I solve this, I'll get it as e lambda d lambda is equal to, we'll get it as e lambda d lambda is equal to, so see here, this c cube get cancelled, this c get cancelled, this h get cancelled. Now lambda also one time it get cancelled. So you are left with 8 pi kt by 8 pi kt by lambda power 4 into d lambda. If you check in black body radiation, this is nothing but Rayleigh-Jeans law. This is nothing but Rayleigh-Jeans law. Okay. So Planck's radiation formula was able to explain about shorter wavelengths and longer wavelengths. It was able to explain about shorter wavelengths and longer wavelengths. Therefore, Planck's radiation law is in good agreement with experimental results for the entire wavelengths. It can explain for entire wavelengths. It can explain for shorter wavelengths and longer wavelengths. So, this is about Planck's radiation formula. Thank you.